This is the 8th lecture on DSP, and today's topic is discrete time Fourier transform. As I have already told you, we shall omit discrete time. We shall simply call it Fourier transform. In the last lecture, we had discussed in detail difference equations, and I told you that difference equations can be solved in two manners. You can have the complementary function, which is the solution to the homogeneous difference equation, and add to it the particular solution. Then you find the constants in the complementary function from the initial conditions. The other method is that you find out 0 input response and then add it to 0 state response. In both of them, you have to find out the constants. In the 0 input response, you have to find the constants from the given initial conditions, and in 0 state response, you have to find the constants from 0 initial conditions. So, you have to do it twice. Finding the constants, you have to find it twice, but since these terms have significance in system theory, they they should have been introduced, and we have done that. We also said that stability can be obtained in terms of the roots of the characteristic equation, which is the characteristic polynomial equated to 0, and that each root for stability should be bounded by unity. It should be strictly less than 1. Then we discussed FIR and IIR, and we illustrated the fact that FIR is not necessarily equal to, this is the symbol that we shall use. NN stands for not necessarily equal to. Now, I think there are two negatives here. Not equal to is already there, so one N should suffice. Necessarily not equal to what? What is the term that I non-recursive? Non-recursive. Similarly, IIR is not necessarily equal to recursive. I hope I have been able to make this point home, because there is a lot of confusion in the literature. Then we discussed an example of a digital integrator, and the equation that we got was y of n minus y of n equal to y of n minus 1 plus t by 2, the average of x of n and x of n minus 1. We took this example and showed that it is an IIR system. We also found out its unit step response. Then we introduced the Fourier transform. FT is so called DTFT, which we have abbreviated as FT, and we defined simply x of e to the j omega as summation x of n e to the minus j omega n, n going from minus infinity to plus infinity. Introduced its parts, that is, it can either be described in polar form in terms of a magnitude and angle, or in terms of the real part and the imaginary part. I also emphasize the fact that the imaginary part is also a real quantity. It is only by multiplication by j that you make it imaginary. And we also stated that both magnitude and the real part, these are even functions of omega, and these are odd functions of omega. The angle as well as the imaginary part are odd functions of omega. The other point that we made is that capital X of e to the j omega is a periodic function with a period of twice pi, and that is the reason why we concentrate on minus pi to plus pi, or because of the evenness and oddness of its parts we concentrate only from 0 to pi. If we know that portion, then we know the total spectrum. We consider two examples. One is delta n, whose Fourier transform was 1, and the other was half to the power n un, whose Fourier transform was 1 by 1 minus half e to the minus j omega. In general, if half is replaced by alpha, some constant which can be real, which can be complex, alpha to the un, alpha to the n un, then the transform, it can be very easily shown that it is 1 minus alpha e to the minus j omega, provided the magnitude of alpha is less than 1. This raises the question of existence of the Fourier transform. The Fourier transform summation must converge in order that the Fourier transform exists. We shall come back to this a little later, but we concluded the previous lecture, 7th lecture, by finding out IFT, inverse Fourier transform, and we said that this is 1 by 2 pi integral minus pi to pi capital X of e to the j omega n d omega. And we also emphasize the fact that both Fourier transform and inverse Fourier transform are not matters of definition. One follows from the other. That is, given this integral, we can find out what is capital X of e to the j omega, or given capital X of e to the j omega, we can find this out. One follows from the other. Now the question of convergence. Convergence of the summation capital X of e to the j omega. Formally, if we take this summation x of n e to the minus j omega n from n equal to minus k to plus k, obviously this sum being finite shall always converge. Agreed? This sum shall always converge. So what we do is we allow k to go to infinity. This must converge. One of the criterion is that the error, if we define this quantity as capital X with a subscript k of e to the j omega, then one condition for convergence is that the error between the actual value x of e to the j omega, which occurs when capital K goes to infinity, minus the finite sum x k e to the j omega, if you take the magnitude and you allow k to go to infinity, then this must tend to 0. The error must tend to 0. This this criterion for convergence is one of the criterion, and we shall show that this is sufficient but not necessary. You see, one of the things, one of the sequences which always shall have a Fourier transform which satisfies this criterion is that x of n be absolutely summable. That is, if this is less than infinity, n minus infinity to plus infinity, if this is so, then capital X of e to the j omega magnitude, which is the magnitude of x of n. This will be less than or equal to the summation. We take the magnitude of x of n. What is the magnitude of e to the minus j omega n? 1. And therefore, if this is less than infinity, then obviously capital X of e to the j omega shall exist. So, if x of n is absolutely summable, then its Fourier transform exists, but this condition is only sufficient. How do you prove that it is sufficient? There are sequences which do not converge, which are not absolutely summable, but their Fourier transform exists. One counter example is good enough, and this counter example is provided by a sequence x of n equal to 1 by n u of n minus 1. If it cannot start from n equal to 0, because you start with an infinite sample, okay, u of n minus 1. Now, it can be shown that 1 by n squared, n equal to 1 to infinity, is equal to this summation converges, that is pi squared by 6, that is the value. But 1 by n equal to 1 to infinity does not converge. Now, obviously, this sequence is absolutely summable. No, it is not absolutely summable. 1 by n u n minus 1 is not absolutely summable, because this does not converge. But 1 by n squared, that converges. Okay. So, this is a counter example showing that x of n absolute summability is not a necessary and sufficient condition. It is only a sufficient condition. Now, this is an example of a sequence whose energy is finite, because 1 by n squared defines its energy, all right. So, we go to the next statement, that is, if x of n is absolutely summable, then its energy x of n squared, obviously this is less than summation x of n whole squared, right. A squared plus b squared is always less than a squared plus b squared plus twice ab. So, a finite and absolutely summable sequence has a finite energy. If this is less than infinity, then its square is also less than infinity. Okay. So, an absolutely summable sequence has a square, is also square summable. Agreed? An absolutely summable sequence is also square summable, that its energy is finite, but the converse is not true. In other words, if you have a finite energy sequence, it is not necessarily absolutely summable, and this was an example. The example that we took, finite energy but not absolutely summable. However, such sequences which are square summable do have Fourier transforms, and in this case what you have to find out is x k e to the j omega magnitude, no, let us take this, minus x e to the j omega. If we take the error squared, limit k tends to infinity, for square summable sequences, obviously this has to go to 0 as k tends to infinity. Have I written this correctly? I have taken magnitude squared, so the negative sign here does not matter, it is a difference. But then this cannot hold. If this holds at all frequencies, even then the Fourier transform may not exist. We have to integrate from minus pi to plus pi. This is our range of vision, and within this range this error in energy must go to 0. This is another way of satisfying the existence of Fourier transforms. That is, first we said absolutely summable sequences have a Fourier transform, but it is only a sufficient condition. Then square summable sequences also have a Fourier transform, and the error criterion is this, that is, the error squared as k goes to infinity in the energy in the frequency domain tends to 0 as k tends to infinity. Now there are sequences, you see, if you don't if you don't take the square, then the limit may not converge, but squared the energy error in the frequency domain converges to 0 as k tends to infinity. There are sequences which are neither absolutely summable nor square summable, but the Fourier transform does exist. For example, u of n, is it absolutely summable? The sum goes to infinity, and 1 squared is 1, so the sum again goes to infinity. Agreed? However, the Fourier transform does exist. In other words, square summability is also a sufficient condition. Absolute summability is a sufficient condition. Square summability is also a sufficient condition. There are sequences which are neither absolutely summable nor square summable. For them also Fourier transform exists. And for the existence of Fourier transform, we have to appeal to the analog delta function. The Fourier transform of such sequences which are neither absolutely summable nor square summable shall have a delta function, the analog delta function. As you know, the analog delta function is defined by 0 minus to 0 plus delta omega d omega is equal to 1, and delta omega is nothing but the limit of this square pulse whose duration is delta and whose amplitude is 1 by delta, so that the area under the curve under the pulse is unity, and when delta tends to 0, small delta of omega, this is omega versus the function, small delta omega is the limit of this square pulse as delta goes to 0. This is the definition of a analog impulse function. Analog, I mean, not in the time domain, it is in the frequency domain, that it is a continuum. Okay. Similar other examples of functions which do not have a Fourier transform if absolute summability or square summability criterion are applied is alpha to the n, not multiplied by un, alpha to the n, and alpha can be any quantity. Similarly, I think we shall have to take, and then e to the power j n omega 0. This is also neither square summable nor absolutely summable. if e to the j n omega 0 has a Fourier transform, obviously its real part and imaginary part which are sinusoidal, that is cosine or sine n omega 0, also should have a Fourier transform, because one is the real part and the other is the imaginary part.
Sir,
Yes.
what did you told that delta omega? What is the relation between un and delta omega? What did you told? I can get it.
Oh, that we shall state. What I am saying is that for such function which are neither absolutely summable nor square summable, the Fourier transform will have a analog delta function. Once you admit the existence of this function, then they are Fourier transformable. And for an engineer, whatever works is good enough. Agreed? Therefore, if we take the help of delta function, a large range of functions are Fourier transformable, and u of n, e to the j n omega 0, sine signal, cosine signal, they do exist. We have to handle them, and therefore we admit a delta omega.
Means in the frequency in the Fourier transform there should exist a delta function.
In the Fourier transform there will exist a delta function. Yeah. For example, let us take e to the j n omega 0. You can show that the Fourier transform of this is given by summation 2 pi delta, analog delta, omega minus omega 0 plus 2 pi k, where k goes from minus infinity to plus infinity. This is an example. E to the j n omega 0 contains a chain of delta functions, okay, at omega 0 plus 2 pi, omega 0 minus 2 pi, and so on and so forth. Proving this in the straightforward manner, that is, you take this function and find its Fourier transform, is not easy. You have to bring in the theory of distribution. But as you know, Fourier transform is a one-to-one transformation. That is, if you prove that the inverse Fourier transform of capital X is x of n, then this is good enough proof. Agreed? Because this is necessary as well as sufficient. It has to be one-to-one transformation, and in such cases it is easier to find the inverse Fourier transform of this. What will be the inverse Fourier transform? 1 by 2 pi integral minus pi to pi 2 pi delta omega minus omega 0 plus 2 pi k e to the power j n omega d omega. This is x of n. Agreed? And in this range minus pi to plus pi, the function, I am sorry, there is a summation here. There is a summation from k equal to minus infinity to plus infinity. In this summation, you have to consider only one term, minus pi to plus pi, k would be equal to 0. This is the base band, and therefore this is equal to 2 pi and 2 pi cancel. This is equal to minus pi to plus pi delta of omega minus omega 0 e to the j n omega 0 d omega. This function exists only at omega equal to omega 0, and I am sorry, 0 should not be there. Therefore, this is simply equal to e to the j n omega 0, because the integral is unity. So, we have proved that the inverse Fourier transform of this summation is equal to e to the power j n omega 0. Okay? In many cases, this is the story. For example, you should prove this yourself. Let us write a few sequences and their Fourier transform. Delta n, we have already shown this is equal to 1. Okay? u of n is a very difficult transform to prove. Oppenheim and Scheffer has a proof. I suggest that you look at it, but again you can go back and prove by taking the inverse Fourier. The transform is 1 minus e to the minus j omega plus a summation of delta functions. U of n is neither absolutely summable nor square summable, and therefore we have to bring in delta functions, and this is pi delta omega plus 2 pi k. Again k goes from minus infinity to plus infinity. One of the ways to understand this is that this takes care of the summation, that is 1 plus e to the minus j omega plus e to the minus j omega, but it does not take care of the average value of u of n. Average value is half, isn't that right? Average value of u of n is half, and the average value is a constant whose Fourier transform is this, and that is why this half comes. That is why this 2 pi, from 2 pi 2 and 2 cancel. Now it is left to you to prove that the inverse Fourier transform of this quantity is equal to u of n. In a similar manner, we have already shown e to the j n omega 0 is summation 2 pi delta omega minus omega 0 plus 2 pi k, k going from minus infinity to plus infinity. And we have of course shown alpha n u n magnitude alpha less than 1 is 1 by 1 minus alpha e to the minus j omega. This table gives you the basic transforms, basic sequences and transforms. Any other sequence can be expressed in terms of these sequences: cosine, sine, any exponential. Then if you have delta functions, they can also be taken care of. Let us take an example. I suggest strongly that you verify this table for yourself with questions like, what will be the Fourier transform of u of minus n, or what is the Fourier transform of alpha n, alpha to the n, u of minus n, and things like that. I have
The properties of Fourier transforms are valid for these also.
For all of them, yes. Properties of Fourier transforms are valid. Once you admit existence of a Fourier transform, all properties shall be valid. Once I admit people to 731 class, they are as good or as bad as any other member, okay? Whether they are tall or short, they wear a black shirt or a red shirt, it does not matter, okay? I take an example, my favorite example, upsampler. Y of n equal to x of n by L, n equals to 0 plus minus L plus minus 2L and so on, and 0 otherwise. The Fourier transform of yn is given by summation x of n by L e to the power minus j n omega, that is the definition, where n shall now be restricted to either 0 or plus minus L plus minus 2L and so on. It of course goes to infinity, but only discrete values of n, the function, the sequence is non-zero. We are not taking the in between samples, all right. What are the in between samples? L minus 1, 0 samples, they will contribute 0 to the summation. And to see what this summation leads to, let us put n by L equal to m, some other quantity which is an integer, okay. Then my summation becomes m, summation is on m, x of m e to the power minus j m L omega, right? M goes from minus infinity to plus infinity, and this fits our definition. This is simply equal to capital X of not e to the j omega, but e to the j L times omega. Isn't that right? E to the j L times omega, and therefore we have shown that for an upsampler the spectrum y of e to the j omega is related to the original sequence, the input sequence, by this relationship e to the j L omega. As an example, a picture is worth 1000 words. Let us draw the picture. Let us suppose that capital X has this spectrum. Well, it has to be repetitive. 0, let us say this is omega h minus omega h, what would be this? Pardon me? 2 pi, agreed, and this would be minus 2 pi, repetition after every 2 pi. Now, if this is capital X of e to the j omega, if I take the spectrum of y of e to the j omega, how does it change? Capital Y of e to the j omega, how does it change? Let us look at that. You see, it would be the same shape, except that this will be omega h by L, and this will be minus omega h by L. The next one will occur at 2 pi by L, and 2 pi by L minus omega h by L plus omega L, and so on. Is that clear? So, the spectrum is compressed. What existed between minus omega h and plus omega h is now compressed to minus omega h by L and plus omega h by L, and therefore up to pi, from 0 to pi, how many such repetitions shall be there? Obviously L minus 1 repetitions, okay. Whereas from minus pi to plus pi there was only one of these samples. In the upsampled version you get repetitions between 0 and pi, that is, in your basic range of vision multiple copies of the spectrum come in, and this creates problems in upsampling. In upsampling you necessarily have to follow the upsampler by a low pass filter, isn't that right, to get rid of all the repetitions, and the low pass filter cutoff frequency must be omega h by L or slightly more than omega h by L, but before the next spectrum starts. Is that clear? So, the upsampler is also a spectrum compressor, and the difficulty with upsampler is not difficulty, the solution to this so called repetition problem, which is also aliasing higher frequencies now poses low frequencies. So, this distortion is also aliasing distortion. So, upsampler has to be necessarily followed by a low pass filter whose cutoff frequency is such that only the baseband signal of the original sequence, only the baseband spectrum is retained, all the rest is deleted. Otherwise, your further processing will give you unreliable results or nonsense results. Before we go further, let us take another example. you are required to find the inverse Fourier transform of capital X of e to the j omega equals to j sin omega. This is an example I took from the book. 3 plus 4 cosine omega plus twice cosine squared omega. This is the problem, to find the inverse Fourier transform of this sequence. Now, obviously, in a general case, we shall have to evaluate the integral 1 by 2 pi minus pi to pi, etc., etc. It is not required here, because all that you require is you are to express this as x of n e to the minus j omega n with appropriate limits of n. In general, it goes to minus infinity to plus infinity. All you require is to find out x of n, that is the coefficients of e to the minus j omega n. This is an example where the the integral should not be used, because you will land in trouble. You should be able to recognize that capital X of e to the j omega can be written as e to the j omega minus e to the minus j omega divided by 2, there is a multiplication by j, multiplied by 3 plus 4 e to the j omega plus e to the minus j omega divided by 2 plus twice e to the j omega plus e to the minus j omega divided by 2 whole squared. And you have got this form now. All you have to do is to simplify this and find out the coefficients of e to the minus j n omega. What will be the highest power of exponential? 3. So, plus or minus? Both. Okay, very good. So, we shall start with e to the j 3 omega, then e to the j 2 omega, e to the j omega, then a constant term e to the minus j omega, e to the minus j 2 omega, and end up in e to the minus j 3 omega. If you can write this form, then obviously the sequence shall be obvious. I suggest that you do this simplification and verify that the sequence becomes, I have carried this out, I do not want to do the algebra here, the sequence becomes 1/4, 1, 4 by 7, 0, and this is n equal to 0. You must indicate where the pivot is, n equal to 0, then you have 9 by 2 minus 1 minus 1/4. This is the sequence that you get. All right. So, given a problem, either to find the DFT or the IDFT or prove a given Fourier transform pair, you have to decide which way to go, how to go about it. Once you understand the problem and find a clue, the rest is algebra. I suggest you do not make a mistake in the algebra either. Now, we talk about the properties of Fourier transforms, which shall be obeyed by all functions which have Fourier transforms. And to do this, we make a table, name of the property, sequence, and its Fourier transform. We shall use two sequences, g of n, small g, which has a Fourier transform capital G of e to the j omega, and small h of n, which is a Fourier transform capital H of e to the j omega. Okay? The first property that we talk of is linearity. Fourier transform operation obviously is a linear operation. In other words, if you take alpha g, I am omitting the argument n, plus beta h, this shall have a Fourier transform alpha capital G plus beta capital H. It is a linear transformation because the definition is simply a summation. So, you take x1 and x2 multiply by alpha, add them, they will give the same. Then a time shift, if you shift g by an integral number of samples n0, then the Fourier transform would be e to the minus j omega n0 multiplied by capital G of e to the j omega. This also follows from the definition. Frequency shift, that is, if you multiply a sequence by the exponential sequence e to the j omega 0 n, then the Fourier transform is simply shifted e to the power j, instead of omega we shall get omega minus omega 0. This also follows simply by writing the definition. You have a multiplication by e to the j omega 0 n, you have a general term e to the j omega minus e to the minus j omega n. So, it becomes e to the minus j omega minus omega 0. Okay. Then differentiation in frequency domain, that is differentiation or multiplication by n, either way. If you multiply a sequence by n, gn, then the corresponding Fourier transform is j dg of e to the j omega with respect to omega. It can be proved also from the definition. For example, you write g of e to the j omega as equal to summation g of n e to the minus j omega n. I am omitting the summation limits, n equal to minus infinity to plus infinity. So, we differentiate with respect to omega. Then in the right hand side we get g of n multiplied by with respect to omega. So, minus j n e to the minus j omega n. Agreed? And if I multiply both sides by j dg d omega, then in the right hand side j multiplied by minus j becomes 1 and we get n times g of n e to the minus j omega n, which clearly shows that this quantity is the Fourier transform of the new sequence n times g of n. Similarly, all other properties follow simply from definition, and I suggest that you carry out this exercise carefully. Let us take an example. X of n is equal to n alpha to the n u of n plus 2. You are required to find out the Fourier transform of this. Now, we know that the Fourier transform of alpha to the n u n magnitude alpha less than 1, this is the Fourier transform is 1 by 1 minus alpha e to the minus j omega. This is the result that I wish to use here. How does the given sequence differ from this? There are just two additional samples. If we take care of that, that is, we write x of n as equal to this u of n plus 2 starts at n equal to minus 2. So, let us take minus 2 alpha to the minus 2, all right. Then the next sample would be, yes, minus, why did I take this minus sign here? Because n equal to minus 2. Similarly, n equal to minus 1, so alpha to the minus 1, and the rest of the sequence is alpha to the n u of n. Agreed? Therefore, capital X of e to the j omega, I go term by term, minus 2 alpha to the minus 2 e to the power yes, j 2 omega plus or minus plus, okay, because n is minus 2, then minus alpha to the minus 1 e to the j omega plus 1 by 1 minus alpha e to the minus j omega. So, this is simply the transform. Given a problem, you must first understand the problem, and that is why I always advise that confronted with a situation, try to understand what the situation, this is in general true in life also. In general, confronted with a problem, try to understand what the problem is. If you understand the problem, then half of it is solved, the rest is pure algebra. Yes. What happened to?
The last extension, the last term.
Okay, okay, very good. There is an n times, let me use a different color, I made a mistake, n times alpha to the n. So, it would be j d omega of this. Yes, I was going to skip this and try to find out if you have found out my mistake. This is what it shall be, okay, because there is a multiplication by n, and therefore the correct Fourier transform would be minus 2 alpha to the minus 2 e to the j 2 omega minus alpha inverse e to the j omega, then plus differentiate this and multiply by j. So, you get alpha e to the minus j omega divided by 1 minus alpha e to the minus j omega whole squared. This is the correct value of the Fourier transform. Continuing the properties, the next property is that of convolution. Convolution says that if you have a sequence which is a convolution of two sequences g of n and h of n, then in the frequency domain the Fourier transform of this is simply the product of the two transforms, and this is a great simplification. Working out convolution in the time domain, as you have realized, is not a very simple matter, but in the frequency domain, if you know the two Fourier transforms, then you simply multiply it. And if you want to find out y of n, which is equal to g of n star h of n, then all that you have to do is multiply this and then find the Fourier inverse, and that inversion may not require evaluating an integral. If you look at it very closely, like a jeweler looks at a given ornament, first he looks at with his small microscope, that magnifying glass. Okay? If you look at it with a magnifying glass, you may not be required to do the integration, but if you have to, then you have to. Okay? There is no escape. Then a property known as modulation. It is also known as complex convolution. Complex convolution. This property is that the two sequences are multiplied in the time domain. The previous case was multiplication in the frequency domain, and it was convolution in the time domain. They are 1 to 1, and this is a dual, that is, the sequences are multiplied in the time domain. So, in the frequency domain it is a convolution, and the expression is 1 over 2 pi integral minus pi to pi g of e to the j omega. This is convolved with capital H. So, e to the j omega minus theta, we introduce a dummy variable, this is to be theta, okay, and then we integrate with respect to theta, not omega. Okay, I should put another bracket here. So, this is a folded version, delayed and folded version, multiplication and then an integration. So, this is called complex convolution, convolution of two complex quantities. Okay. Finally, Fourier transform also gives an easy way of calculating the energy of a sequence, and this is given by the so called Parseval's relation. We will first state the general Parseval's relation, and that states that summation g of n h star of n over all possible values of n equal to minus infinity to plus infinity, it states that this is equal to, let me write it specifically, n equal to minus infinity to infinity. It states that this is equal to 1 over 2 pi minus pi to pi capital G of e to the j omega multiplied by h star of e to the j omega d omega. This is the generalized Parseval's relation, where obviously we have assumed that both g and h can be complex. Okay, that is why we put a star. Now, a special case of this, special case is g of n equal to h of n. Then you see the left side becomes g of n squared, magnitude squared. Okay, g of n, g star of n is magnitude squared, n equal to minus infinity to plus infinity, and this would be 1 over 2 pi integral minus pi to pi capital G multiplied by capital G star. Star is complex conjugate, therefore g of e to the j omega magnitude squared d omega. The left hand side is energy in the time domain, and the right hand side is the energy in the frequency domain. The two energies must be the same, because Fourier transform is 1-to-1 transformation. No property shall be destroyed by taking this set from the n domain to the omega domain. Generalized Parseval relations. I shall conclude the class with some symmetry relations, and this also I strongly urge you to prove each of them. The proof is simple, particularly in the first two cases. It may not be so in the later ones. It says that if x of n is capital X of e to the j omega, then x of minus n is capital X of e to the minus j omega. Is it obvious? X of minus n e to the minus j n omega, you put minus n equal to r, then obviously that becomes capital X of e to the minus j omega. The next relation is, if you take the complex conjugate of xn, xn is a complex, if xn is a complex quantity, then the corresponding Fourier transform is x star of e to the j omega. This is also not difficult to prove. Okay. The real part of xn, if xn is complex, then it would be given by, this is also not difficult to prove, real part after all is x of n plus x star of n divided by 2. So, this is why this half comes, then capital X of e to the j omega, and x star of n we have already said, so plus x star of e to the j omega. Similarly, the imaginary part j imaginary x of n shall be half of this minus this. Okay. one of the things that people often make a mistake is, suppose you are required to find out the Fourier transform of imaginary part of x of n. It's a real quantity. Imaginary part of x of n is a real quantity. So what you have to do is you have to take j to the right hand side. Agreed? Do not make a mistake. Imaginary part, unfortunately, the nomenclature is such, it is called imaginary part, but imaginary part is also a real quantity. And this is where I should stop.